Hello, everybody, and welcome to Solving Electromagnetic Challenges, an EMA webinar series. My name is Matt Colding, and I will be your host for today's presentation on Space, Environment, and Radiation Effects Lab, Capabilities and Roadmap. Please be advised that to submit any questions that you have today during today's webinar, you should please use the Teams webinar Q&A feature. After the presentation, we will address any submitted questions. Should there be any unanswered questions at the end of the webinar, we will address them over email. Our speaker today is Brian Wood. Brian received his master's degree in physics from Utah State University in 2015, where his research focused on the synthesis and optical characterization of carbon nanotube forests. Following graduation, he joined the Space Dynamics Laboratory, contributing to the development of a neural particle beam emitter designed to simulate atomic oxygen ablation processes experienced in low Earth orbit. He later returned to Utah State University to join the Material Physics Group within the Physics Department, where his research addressed key challenges in spacecraft charging. During this time, he collaborated on and authored multiple studies examining the effects of radiation on both passive spaceborne materials and powered components, with an emphasis on how ionizing radiation and total dose exposure impact material properties and system performance. In 2020, Brian joined EMA as a scientist, where he led the construction and development of the Space Environment and Radiation Effects SERE lab. Today, the SERE lab supports both the validation of EMA's simulation software and the commercial availability of radiation testing and measurement services for space applications. Without further delay, I give you Brian.
Great. Thank you, Matt. So as Matt mentioned, I've been with EMA for about 5 years, and I've kind of overseen the development and all the projects that go through the SERE lab. And so this presentation will just kind of serve as an outline for the stuff that we are capable of doing for customers, some of the things we've done in the past, and any of the future capabilities we're currently working on. So just to give you a little bit of an overview, the SERE Lab's located in the Berkshire Innovation Center, which is located in Pittsfield, Massachusetts, which is Western Massachusetts, located in Berkshire County. So we started development of the lab in 2020, and we essentially became operational in 2022. We were able to undertake projects by then. And the funding for the lab came not only from direct contribution from EMA, but we've also received contributions from the city of Pittsfield and also just grants supplied from state funding as well. And so that's been really instrumental to get us going and was a really nice step to kind of become self-sustaining with the work that we're able to do through project work. And so the SERE Lab, Space Environment Radiation Effects, we essentially have a spacecraft charging focus for the projects that we carry out. And so that's considering the space environment, that's essentially sort of the low energy, high flux portion that kind of mainly dictates the charging behavior of your spacecraft or your instrument or a given material. And so basically what we can offer, you know, a lot of different capabilities for a customer, but it usually starts with the customer coming to us with a desire to do a test, and we work with them to develop the test procedure and establish the experiment so that the customer gets the results that they need to qualify or understand the risk that they might be running into for their specific situation. And so a lot of the things we do are very custom, very niche, and it's kind of hard to give direct examples of what we've done, but I'm just going to kind of overview sort of the individual capabilities that we've got, and kind of paint you a picture of what we're able to accomplish with the instrumentation that we have. And so we've got essentially a main vacuum test chamber. It's about a cubic meter in volume. It's about 5 feet long, 3 feet in diameter. That top right picture, you see the sample plate. That is a 24-inch sample plate, and so that's essentially the max size of an object we can mount inside the chamber. And what the projects we undertake essentially boils down to is just loading the instrument or material or whatever it is, the sample under test, in the test chamber. And then we irradiate it with our radiation sources as per whatever test procedure we've decided on. And we kind of measure the charging behavior and simultaneously measure any arcing behavior that occurs downstream with traditional probes and oscilloscopes. And so that left picture, you see our radiation sources. And so we have two directionalized electron guns. They're flood guns, and so they're wide, fairly uniform beam sources, and we have a 30 keV electron gun and a 100 keV electron gun. And so each one of those can sweep, anywhere from, say, a few hundred EV all the way up to their max energy. And those are essentially the workhorses for the projects that we do, since the electron flux is essentially what's dictating the charging behavior in the space environments. But we do also have a 100 keV proton gun, and so that recently became operational, and we're excited to be able to use that with some upcoming projects, and be able to give sort of a full representation of the space environment with these sources. And so what's unique about that proton gun is that that can actually be ran simultaneously with the electron guns, which can also be ran simultaneously with each other. And so we can kind of have this, these mono-energetic sources running at the same time, hitting the sample and trying to understand the charging behavior. And so also for the radiation sources, we have a plasma generator. And so that's sort of the lower energy, kind of high density plasma soup that you might experience in low Earth orbit. And so that's essentially a low Earth orbit simulation plasma generator. And with those, we kind of cater how we use those to sort of simulate the specific space environment that's of concern. And so we use those radiation sources. We have other measurement probes, and so we have the Langmuir probe to characterize our plasma when using the plasma generator. We have a Faraday cup that's always mounted on the sample side to monitor the flux of the electron guns or the proton source. We do have a surface voltage probe, and so that's a non-contacting electrostatic probe. So you can charge up your instrument or your material, and then we can sweep that across the sample to measure what surface potential it's reached due to some incoming radiation. And that's located on a Z stage that allows us to sweep it up and down across the sample. Also in that top right, you see an XY stage that we can use either for specific probes, like there you're seeing the Faraday cup mounted to it, which we use to map out the radiation sources, or we could use that for sample manipulation or anything else we need. Finally, we also have a cryocooler, so we do have the capability of mounting the sample fixture to the end of that cryocooler, and that would allow us to do some cold temperature testing without power load. That would essentially get down to 40 Kelvin if we wanted to. And so that's something that our customers are also eager to use for their projects. Just a little bit more detail on the radiation sources. The low energy plasma system, or LEPS, is basically that LEO simulator. You get ion energies between 20 to 40 eV. It's got sort of a magnetic filter incorporated into it, and so what that does is it's only allowing these kind of sub eV or 1 eV electrons through the plasma generator, and that's to help better simulate the LEO environment. And the densities can range anywhere from, and these are kind of rough numbers, but 2 times 10 to the 9 to 3 times 10 to the 12 particles per cubic meter. And that kind of depends on, which gas we choose to feed it with. We usually use argon. We've used xenon before. But we kind of choose these densities to, again, try to represent whichever environment the customer is looking for. So there's typical LEO densities. If you're trying to go really low to try to represent sort of more interstellar densities, we can do that. If you want even higher densities, that is a concern sometimes if you're in LEO and you're operating a plasma thruster, where that plasma thruster is actually contributing to the ambient plasma around the spacecraft, then you would try to use this device to simulate that. And so there's a couple of the beam maps for the 30 and the 100 keV gun, just for reference. So this is something we usually always do prior to a project to make sure that the beam map is where we need it to be and that it's uniform. The electron gun themselves, they can go up to, we say, about 10 nanoamps per square centimeter for the flux, but our measurement with the Faraday cup can be as low as 1 picoamp per square centimeter. And so our noise floor is low enough that we're able to accurately determine, when we're irradiating with those sort of lower fluxes, which are usually more indicative of sort of the in situ values that you see. Unfortunately, I wasn't able to provide a beam map for the proton source. We just got that up and running in February 2025. And so some characterization still needs to be done on that, but that's something we're in the process of doing. So instead of kind of going over some example projects we've done, I'll just kind of discuss some of the typical charging scenarios that we do. And so one of those is kind of just this direct charging of a dielectric, that the dielectric portion of the sample that you're providing us. And so essentially that's just mounting the sample in the chamber onto the mounting plate. And you are irradiating that with the higher energy electron guns. It can be a single source or a dual source. And while that's charging, we do have the capability, like I mentioned earlier, to sweep the surface voltage probe across the sample. We are simultaneously measuring the flux with the Faraday cup. I didn't mention it earlier, but we do have a camera that's pointing at the sample, and with some capture software, we're actually able to capture any arcing behavior that is visible. We can capture those with that camera really well, and so that's kind of the cool part of these projects, is being able to capture the visual signature of the arcing behavior. And like I mentioned before, we're capturing any arcing signatures, and so whatever we mount the sample to, we isolate that from the chamber ground, and then we feed that signal out of the chamber through an SMA feed through. And in series with that, we'll just have a typical current probe, and we terminate that line to ground with 50 ohms typical, but depending on the situation, we can change the external circuit to match whatever is needed. This is just kind of a typical setup to kind of capture the current voltage waveform associated with the discharge. And so so this scenario is the term normal potential gradients kind of more reserved for solar panel testing, which I'm going to discuss later. But essentially, it can kind of generally be used when the dielectric is sort of charged more negative relative to any nearby conductor or substrate or whatever the conductive portion of the sample is, which in this case is essentially grounded. But and so it's kind of like just direct dielectric charging, to think of it that way. And so with this scenario, you've got your sample in there, you've got your electron sources. How do you decide what energies and fluxes to shoot the sample with? And that's where we essentially look at the specific space environment that the sample will experience. And so this plot here is an example of how we kind of determine the energies and fluxes that we choose to irradiate with. In this case, this is the differential current density of transit electrons. And so with this, since we, space environment's a spectrum, that's a whole range of energies, we're not able to perfectly simulate the environment in the lab, unfortunately, is one of the cons. But what we do is essentially just bin up the energies into two bins, and we use one energy to represent that entire bin and another energy to represent the other bin, and we will integrate the area under that curve to choose the flux to represent that bin with. And so essentially what you want to do is kind of, if you're trying to do sort of an in situ type of exposure where you're trying to sort of accurately represent what the sample is going to be receiving, in that moment. This is the method we do, where we essentially plot the differential flux, separate the energy bins, integrate to get the flux to radiate with, and choose which energies to irradiate with. And so we typically, some of the typical things we've done is just, going to 100 keV max for a 100 keV gun. For this instance, we picked 20 keV to represent the other bin. And that's sort of a normal scenario for us if we're doing this type of charging. So another typical scenario, and I'll mention now we're talking about inverted potential gradient. Again, this is, I'm kind of using this term generally, even though it's kind of particularly used for the solar panel testing. But now this is the scenario where the conductor is now charged more negative relative to the nearby dielectric. And so what this can be, what this kind of represents in sort of real scenario is, say you've got a satellite that's in geo. You know that if you got a satellite in geo, the chassis is charging highly negative. And so the conductors of your sample, in that scenario would be highly negative. But then once, say, the front face of that spacecraft gets exposed to the sun, you start getting some charge neutralization of any exposed dielectrics that might be either touching or nearby the chassis potential conductor. And so now that dielectric is sort of becoming less negatively charged relative to that chassis potential, and then you start developing differential potentials that could exceed the breakdown, and you can start getting arcing behavior. And so how we simulate that in the lab, one way of doing it is essentially you've got your sample mounted. It could be, some dielectric with a conductive substrate or a conductive frame or whatever it is. And now you are directly biasing that substrate of the sample with a high voltage supply, biasing it negative to represent how it would charge in the environment if it was geo. And simultaneous to that kind of biasing of the substrate, you are then exposing the sample to some plasma or some low energy electron exposure to sort of neutralize the front surface of that sample. And so the LEPS is a really good source for doing that. It's basically just a soup of electrons and ions. Those will be attracted to the sample. They'll neutralize the top surface, and you can start induce arcing that way. And this is a really controlled way of doing this test. And so you are controlling the bias. And so it's a really good way to slowly increase the bias and see when you start to see arcing, and determine sort of the voltage threshold for arcing. There's another way to, instead of using the LEPS, you can irradiate with low energy electrons and exploit the secondary electron yield of the material. And so you're basically charging that front surface more positive by just exploiting the secondary electron yield. And likewise before, for monitoring arcing, in this situation, we also have the current monitor, the current probe in series with that signal line. In parallel with that, we do have I'm showing a 2 nanofarad capacitor. That's put in there to sort of help represent the capacitance that might be associated with the arc. So there's always going to be some capacitance that's contributed from the spacecraft relative to plasma, and that's going to be usually a really low value. But sometimes you might add more capacitance if you know, hey, I'm giving you this sample, but the sample is kind of only a small representation of what it's going to actually be. So say the sample might actually be a much larger sample on the spacecraft. You can only fit so much in the chamber. And so we'll kind of add additional capacitance to try to represent the real kind of LCR components of the sample in the actual spacecraft configuration. And so similarly, we also have a voltage probe across that capacitor, and this is just a way to monitor the current and waveform captures. And so those are kind of the two general broad scenarios of charging. Again, there's lots of different ways to exploit this for your particular project. And that's kind of where the catering comes into. You come to us and you say, hey, I want to do this, and we discuss it, and we figure out how we configure the chamber and the test and the mounting and the fixturing to achieve the results that you want. So I did mention, it's hard to come up with direct examples of some of the work that we've done, but some of the things that we've done multiple projects on is this ISO 11221, which is the solar panel ESD testing. And so for those who aren't aware, essentially, if you've got a solar array, that's going to have special plasma interactions with the space environment, because now it's its own power source, it's providing its own bias, and it interacts differently than just, say, other passive components. And since it's also the power supply for your spacecraft, a lot of attention has gone into the solar panel ESD testing, and for a good reason. And so as people were using solar arrays in space, sometimes they were getting these catastrophic failures, and it was determined that you'll send a spacecraft into space, you get arcing on the spacecraft, which is kind of always going to happen, and in this context we kind of call those primary arcs, where you get these arcs that are kind of happening over it, and they're small, and they're usually not too detrimental. But what can happen is that primary arc will happen right in between the gap in between two strings, And now you can possibly create a bridge between those two strings, and depending on the voltage between those two strings and the possible current that can be supplied behind that arc, you can form sort of a permanent arc across that gap. And so this was discovered early on, and since it's got such a high risk associated with it, people really want to investigate this. And so that's one of the tests that we are comfortable doing here in the SERE lab, where you give us a solar coupon, which is a representative coupon of what you might send up into space, and we load that into the chamber, and we will start to bias the strings to kind of simulate any charging that would occur on the chassis. We expose it to the low energy plasma, and we start inducing these little primary arcs, and then we start to see if any of those are producing any type of sustained arc in between that gap there. And so that is this plot on the top left here is basically just one of the direct waveforms of one of those interactions. And so that purple line, IFO, stands for the flashover, which is essentially the waveform of just that primary arc. And so we can dictate the strength of that primary arc to help it be more representative of an entire array. And as we run this test, we'll get a primary arc, and then we're also monitoring the current that's going through those strings. And essentially, you're able to determine if there is any amount of current that's going across that gap that persists past what the primary arc is providing. And so that primary arc is essentially providing the plasma to connect those two and form that bridge. But then once that primary arc ceases to exist, you would hope that the sustained arc would also stop. And that's this waveform that you see here is an example of that, where you see the IFO stopping, and you see all the other currents kind of going back to their nominal values. And that's what you want to see. What you don't want to see is that primary arc ending and then those currents persisting. And they can persist for, if you're looking at the time scale here, that flashover is lasting, over 1,000 microseconds. If that flashover ends and then that sustained arc persists for thousands more of microseconds, then you've got a sustained arc. And then you look at your design of your solar array, you say, hey, maybe my gap is too small, maybe I'm running too large of a differential voltage between these strings, or maybe I'm running too much current between the strings. And so that's the main goal of this test is someone who's designing a solar array. They want to be able to cram as many strings and produce as much power as they can. But there's going to be some limitation to that based off of this effect. And so we're able to provide this testing, all the analysis, and any visual signatures. As you can see here, that was an example of one of the sustained arcs we got, and provide that to the customer and help them sort of determine which areas are risk and which areas are safe when it comes to their design. And so it's not really also just about determining if secondary arcing is going to happen. It's also kind of seeing if there's performance degradation just as a function of any of these primary or flashover arcs happening, or if there were sustained arcs but they were fleeting, how did that affect its performance? And so we always do here in the lab, we do dark IV measurements to pre and post to see if there's any performance degradation due to the arcing, and give the customer that key piece of information. Another example of something we can do that's also included in the ISO 11221 is this LEO plasma leakage current. And so say you've got a satellite that's operating in say fairly high plasma densities, and the array is, in operating in the hundreds of volts range, that array can directly couple to the plasma and basically just leak current out into the plasma. And so that's seen as a current draw from your solar array. It's drawing power away from the spacecraft, and um, that's something that's undesirable. And so that's another test that we can do, where essentially you're just kind of trying to operate or bias the coupon at typical voltage levels, and then you can tweak the current densities that you're exposing it to see what leakage levels you're getting and what densities would result in sort of compromising leakage levels. And this is becoming more of a concern with the electric propulsion movement that's kind of going now, where we're trying to, maximize the weight to fuel ratio. And so people are doing these slow orbit raisings with these plasma thrusters, which is, it's a good idea, but it can also provide sort of additional contamination or plasma ambient to the spacecraft, and kind of can enhance that leakage current issue. And so that's something that we're also able to investigate. So overall, this is, one of the main capabilities that we're able to do. It's a big one because it's kind of always a concern with new developing types of solar cells, or if people are trying different designs of their solar arrays and they think there might be an issue. This is something we're able to do for them. So moving kind of away from the main test chamber. So the main test chamber, there's lots of use cases for that, and a lot of that just kind of depends. I've given kind of a general overview, but it really just depends on what exactly you're trying to do, and that's where just a phone call to us is worth a million words, because we can just kind of tell you right off the bat if we're able to help, and how we would go about it. Some of the other things we can do is UV aging. And so here you can see this is a little load lock chamber that we've got. It's kind of just a general purpose chamber, but here you can see we've got, we took 4 micro discharge arc lamps, and we basically just put them in a single housing, and we attached that to this chamber, and we kind of measured to see how much UV we're producing in comparison to AM0. And so UV aging, there's lots of possible needs to do this for specific materials. And so we just went ahead and made this accelerated UV source. It's shining through a fused silica window into this chamber, and we used, our little spectrometer to measure the spectral radiance of the source. And so that bottom graph is basically the AM0 there in purple, and our UV source, where the AM0 is scaled, in this case 273 times, just to kind of give you sort of how much it actually matches the AM0 per wavelength. But essentially what this means is, we're able to age things times 270 amount, compared to the AM0 flux that you would see. And so that 270, it can be increased, it can be decreased just by changing the distance of the sample to the sources. But this is just a good little source we've got that's able to do decent acceleration. If you're trying to do age 5 years or something in geo, we're able to do that relatively quickly. We can do peel off tests where you essentially put multiple samples in there and you peel them off at discrete times, or we could integrate other measurement in here. My next slide goes over our spectroscopy, but you could try to see how a material might be degraded over time with repeated reflectance and transmission measurements kind of in between this exposure. And so a nice little capability we've just gotten up and running. We do have sample cooling associated with this. The sample does warm up a decent amount, and so if you're worried about that, we are able to cool the sample while it's being irradiated. I mentioned before, so we do have some spectroscopy capabilities, and so we've got a couple of stellar net spectrometers that range from 200 to 1700 nanometers. We do also have a mid-IR spectrometer. And depending on what you're trying to do, so one use case is basically optical coatings where people will give us a window with a specialized optical coating that's, going to be exposed to the space environment. We're able to irradiate the coating and the lens in our main chamber, and then depending on the measurement you want, we can actually even integrate reflectance or transmission capability into the chamber. So we were able to do periodic reflectance measurements while we're irradiating it. And so that's giving you that kind of in situ change or degradation of your optical coating as a function of dose that it would be receiving from our electron sources. And so our electron sources go up to 100 keV, like I said. So the aging can kind of only really be done to these thin films, but this is something we've done in the past, and that's just one use case of these spectrometers. It's just something that we've been able to incorporate with some of our past projects that I wanted to let you know about. So apart from the main chamber and some of these other capabilities that we're able to either integrate directly with some of the main chamber testing or just stand alone is our material characterization. And so material characterization essentially just means determining what the material property actually is for a given material. And so the biggest one really is just the secondary electron yield, where that is sort of the direct measurement of how a material will charge due to incoming electron irradiation. And so for those of you who aren't familiar, basically you load a sample into this chamber. It uses a hemispherical grid retarding field analyzer, which is basically just a dome that's sitting over the sample. You pick an energy, electron beam with a single energy, you shoot it at the sample, and you're measuring how much current is going into the sample, and you're measuring how much current is coming off of the sample. And so you can shoot electrons at a material, and either they could all go in there, or they could actually excite electrons in that material and give them enough energy to escape the material. And so you can actually charge something positively with an electron beam, and the secondary electron yield measurement is the measurement that tells you what that yield is for a given electron energy. And so this plot here is basically the secondary electron yield of HOPG, or just highly ordered pyrolytic graphite. And so our results are the green, and they agree reasonably well with some of the historical data that's out there. And so this is really nice system we've got. We can have high throughput, meaning you can give us several samples and we can kind of crank through those measurements relatively quickly. There is difficulty with trying to measure insulators in this system, and so at the moment we can do conductors, but we're going to be able to do insulators in the very near future. And along with that, we're also going to be able to accomplish photoyield measurements. And so we've got a flow lamp that we're able to tune the wavelength of the photons that are going into the chamber and hitting the sample. And you can actually produce essentially the same plot, but not for electrons as the incoming radiation source, but photons as the incoming radiation source. And so So also the constant voltage conductivity, so basically how conductive something is. And this is a fixture that we quite haven't got this system going yet, but we've made the fixture for it. And that's essentially pretty straightforward. You're just sandwiching the material, you're applying a voltage to it, and you're measuring the current across it. And based off of the geometry of the sample, you can just calculate the conductivity or the resistivity. And so pretty straightforward in theory. The problem is that you're trying to do this to extremely insulative dielectrics, and so you need to do this in vacuum, reduce all the noise in your system, and you need to have a very sensitive electrometer. You need a battery power supply so that there's no ripple in your applied voltage, and after all that, you're able to accurately measure the conductivity of these insulators that are commonly used in space. And so I mean, so like, why is this important? Is because these two material properties, there's a plethora of others that are used in software simulation that really dictate how a material charges in space under a given exposure. And so uh, it's really important to know what those values actually are for a given material. And um, so, people have taken data on, common materials like Kapton and polyethylene and Teflon. And so that data is all out there, but people are always coming up with new materials. They're coming up with composites. And there's just kind of always going to be a need to have this capability because of the development of new materials that are being implemented on your spacecraft. And so that's why it's really important. Also, EMA is a software simulation company, and so we have a product, Charge Plus, where you're simulating how spacecraft and instrumentation and materials charge up. But you're supposed to input values for these material properties, and so how do you know what values to put in if it's sort of an unknown material, or if it's hard to track down the data for it, or it's something that you're developing and you're saying, I don't know what to put in for this. And you can't really believe your simulation as far as the material properties. And so it's kind of critical to really at least have some idea of what these values are. And so being able to directly measure those is pretty key. So that's about it. And, I've given a general overview of what sort of the main test chamber in the SERE lab can do, some of our other capabilities, how those could be integrated into some of the testing you want, and, a review of the material characterization and its importance. Yeah, thank you all for joining, and I'd be happy to answer any of your questions.
Okay, thank you, Brian. Let's take a moment to review the questions we've received. The first one here is, what do you have planned for future capabilities?
Yeah, so I didn't really have a slide for that, but we are kind of continuously developing, added capabilities, whether it's new standalone things or something to enhance the capability of the main test chamber. One of the standalones is not totally related to space environment testing, but it's laser-induced damage threshold testing. And so this kind of goes a little bit along with sort of the optical testing we're able to do. And essentially, that's just a capability to measure how much energy from a laser pulse it takes to start to deform a coating or a lens that's given to us. And so this is, kind of a common test that's part of just sort of a optical characterization suite. And it can be used in conjunction with some of the stuff that we do with the main test chamber, where say you've got a coating and you want to see how the aging might affect its durability. That can be something we can do where we age the material or the lens in the chamber, and then we do this LIDT testing to see, um, you know, if it's had any effect on that. Another big one that we're doing that's in conjunction with the main test chamber is trying to provide higher energy electrons as part of our irradiation suite. And so, as I mentioned, we can go up to 100 keV. We've got dual sources, which is really good to be able to um, more mimic the space environment, but we were kind of lacking in the higher energy portion. And so we are developing and having a strontium-90 source built for us, and essentially that's just going to be an array of strontium-90 pellets that will be in, a custom housing, and it'll just have a gate valve shutter, and so you would load, and that would be integrated into our load lock chamber. Essentially, like I showed, where that UV source was, we would just bolt on our strontium-90 array. You would load the sample in there, you would expose it. You could do in situ measurements in that load lock chamber if you wanted. And the beauty of that load lock chamber is that if we wanted to then do some of our 100 keV electron testing, we would essentially, with that load lock chamber, be able to irradiate the sample, the strontium-90, and then remove the strontium-90, move that load lock onto the main test chamber, and then insert the sample into the main test chamber and do some ESD testing post-aging, say, and with no exposure to oxygen. And so that's another one of the big capabilities that we're developing.
Great. Okay, next question is, what are the costs and availability of this kind of test service?
Yeah, so the cost is, it really just depends on what you're trying to have us do. If it's like a whole ISO campaign, that's going to be more than if you just asked us to do some UV aging for you. And so the cost, you can't really say. That's just a discussion that's dependent on what your needs are and how difficult it is for us to undertake. The availability, there's always need for the chamber, and we do work to try to juggle things around and make things as best as we can for our customers. Uh, of course, kind of during our discussions, you don't really fully get reserved into the chamber until we get issued a PO. And so sometimes the PO process and the proposal process can take some time. And so it's just, it's something that we're in constant communication with our customers with the scheduling of the chamber and just trying to make sure that we're able to get people in when they need to, and just make everyone happy. So that's a hard question to answer, but it's something that we just work with the customers on to get done.
Great. Next question, is that a STIB proton gun?
It is. So all of our proton sources are from Stabe, and they've worked out pretty well for us. And they've got good customer service. Their local office, or the people we work with, is in Pennsylvania, and so they're relatively close to us in Western Massachusetts. And so we've always had good luck with them. That's also the source that's used for the secondary electron yield chamber. And so, yeah, so pretty much all of our radiation sources are from STIB.
Great. I believe this question is with respect to a slide you showed earlier in the presentation, but somebody's asking, are those solid black lines 10% uniformity lines or something
Mm.
else?
Yeah, so maybe I didn't hang out there long enough. So the left one is relative percentage, and so yeah, you can see that black line. That one is at 5%, and so and then the dotted is 10%, and I believe that's also the same case for the right plot, which isn't graphed as relative percentage, but the actual current density. But yes, the black is 5% and the dotted line is 10.
Okay. Can various orientations relative to the RAM direction be simulated in the test setup?
So yeah, they're referring to just you've got a spacecraft in orbit. If you are, say, coming directly incident to the sun, you might be getting more of a photoelectric effect as opposed to if you're skewed to the sun. That's not really sort of how you would handle that question. Essentially, what we would do is, like I say, we are just accurately determining the differential potential that's created during the test. And so to try to correlate, this is actually a good question because what we try to really do when we take on a project is we try to merge both the software simulation and the physical testing as much as we can. And so in that situation, what you would do is you would and this is usually the case, you sort of start with a software simulation to determine how the factors like what you're asking or anything else can have effect on the differential charging of the spacecraft or the component. And then what you do is once you've determined that differential charging or potential, then you try to mimic that in the lab the best you can. And so um, so yeah, that's a situation where you're kind of to get that level of detail with your test, it kind of requires some level of software simulation to set bounds on your testing, and that's what you rely on to try to accurately represent the environment.
Great. Next question is, can pre and post thermal optical property measurements be done on materials exposed to the UV aging testing to get a measurement of solar absorptivity and IR emissivity at the end of mission life?
The let's see, the absorptivity possibly. So essentially, we basically just deal with the sort of, we use integrating spheres to take these reflectance and transmission measurements. And so those are essentially the total hemispherical diffuse reflectance and transmission measurement. From that, if you took both of those, I think you can get the absorptivity of the sample. The emissivity, that's something we haven't dealt with. And so that one I'm not totally sure on if we're able to do that with this specific set of equipment. But so essentially we're relying on essentially what we've done before, and what we're comfortable doing is basically diffuse reflectance and transmission differences pre and post exposure.
Okay. Next question is, given your background in ATOX, are there any plans for an atomic oxygen source for testing low LEO materials where that would be a concern?
Um, I would say no. There is, we would be able to coordinate that effort, but to develop our own, that would be sort of a significant effort on our part. And so we've looked into what it would take to sort of develop that because, you know, as you mentioned, that's one of the things I did at JPL. That's a pretty big undertaking, and I didn't think it quite fit in line with how we wanted to, you know, use our funds. And so we did look into where those facilities are, and there are some nearby, and we've, you know, even contacted them. And so if that was something that people were interested in, we could help coordinate that. And if they needed that done in conjunction with some of the testing that we do, you know, we'd be happy to coordinate that and see if we can help them out there.
Great. Next question is, how will you measure photo yield?
So I briefly talked about that, but essentially that would be, where is my, essentially we've got an arc flow lamp, and we haven't installed it yet, but that would be integrated into the secondary electron yield chamber. And so that would, the flow lamp lets us, pick out a specific wavelength out of the flow lamp and shine it at the sample, and then still using the HGRFA or that hemispherical grid analyzer, picking out or determining how many electrons are coming off for a given light flux coming into it at a specific wavelength. And so it's basically using the same setup of the chamber in the HDRFA, but now the source is just a flow lamp that we currently have, that allows you to, the flow lamp is a continuous source, but we're able to pick off mono-energetic portions of that and shine it into the chamber and hit the sample.
Okay. Next question is, how do you measure the dark IV curves that you mentioned before?
Yeah, so essentially so dark IV is just, the sample's not illuminated, and you're just biasing the sample, you're sweeping the sample and you're biasing it. And so it's not really an ideal way to check the performance. It's kind of a cursory test to look for degradation. It checks for major degradations, but essentially it's not an illuminated performance test. And so basically you are essentially, reverse biasing the string, and you sweep it through whichever voltage range you're allowed to for the given string, and you're seeing the current response. And so it's, yeah, like I say, the dark IV is just kind of, it's something that we're able to do in the lab since we don't have really an illumination source to be able to run sort of a proper performance sweep on it. And so we just rely on the dark IV in that sense.
Okay. We have some other questions here in the chat. I'll try to get through as many of these as we can. First one is, how do you create the flashover waveform for the solar panel ESD test, as there are many methods of creating this?
Yeah, so I'll use this circuit as an example. It's basically an external LCR circuit that's in parallel with the biasing of the solar coupon, that is dictating the waveform shape. And so here you've got the power supply, and that's biasing the sample, but in the case that would be the coupon, and I've got this 2 nanofarad capacitor there. Essentially now what you also do is just put an inductor and a resistor in series with that to dictate the waveform. And so that's how we create it. It's sort of, it's basically just adding these LCR components to the discharge circuit so that when it does primary arc, those components are providing the energy and the wave shape that gets blown off into the plasma. And so that's what's producing the blow off. How we determine the size of that kind of depends on the size of the array. And so the flashover waveform is essentially a complex waveform in reality that's dependent on the capacitance of all of the solar cells relative to plasma, with the cover glass as the dielectric. And so there's lots of papers out there that discuss the derivation of the flashover waveform. And it is pretty complicated, but essentially what you're doing is just trying to calculate what your maximum flashover waveform would be based off of the size of your solar array. And then that's what we use, that maximum is what we use as the primary arc, because that would have an effect, on the ability to generate a sustained arc. And so it's kind of a way of using the worst case flashover waveform to act as the primary arc that could instigate the sustained arcing.
Okay, great. Um, Unfortunately, it is time for us to conclude this session as we have now reached the end of the hour. As a reminder, any questions that we did not answer today during this presentation will be addressed via email. Following today's webinar, all registrants will receive an email from EMA with a link to the recording of this presentation. And if you have any questions about a particular section of interest, please feel free to reach out either through the ema3d.com website or over email. Next up in the EMA Solving Electromagnetic Challenges webinar series is Full Vehicle Simulation for EMI EMC, which will occur on May 21st at 11 a.m. Mountain, 1 p.m. Eastern. Thank you all very much for your time and attention, and have a great rest of your day.